so we don't lose one. Okay, 2 recordings, perfect. We're in. All right, welcome everyone. This is lecture 5, Arithmetic and Pipelining. We'll be going over math today and how to pipeline it to make it faster. Pipelining applies not only just to the math that we do, but a lot of the operations we use will be mathematical. So let's get right into it.
Alrighty, let's start with some club-wide announcements. This Wednesday at 6:30 p.m., which is tomorrow, we have our IEEE General Winter Meeting. This is going to go over pretty much how IEEE is going to look for the rest of the quarter. It makes Taylor happy, and make sure that Taylor's not mad at us. That is all.
All right, so I don't know if the people that finished Lab 4 are here, but if you finished or you're still working on it, kudos to you, because I care that you tried a lab that, even though we didn't make it mandatory, hopefully was fun. Some people did finish it, and something that we learned was that when you work with buttons, especially, well, just buttons, you have to work with making sure that, like, since a clock is running much faster than the human button press, you have to think about how long the button's on for and make sure that you're only registering each continue in a state machine for 1 clock tick. Otherwise, if you keep continuing, it might just push through states super fast. So you'll skip a lot of states in the process. So if you're still working on the lab, let us know when you complete it, send us a video, and we'll be happy to check you off, get you the extra lab bucks from last quarter. And that's all I got for Lab 4. And in addition to Lab 4, over break, we wanted you guys to fill out the survey from last quarter. And a couple of things that came up were that you wanted more explanations in lecture for the spec. So we'll be doing that a lot more this quarter, trying to explain how the concepts in lecture connect. But also keep in mind, what we're trying to do is the lectures are supposed to be conceptual so that they help give a general understanding of the concepts in our labs, but we want you guys to go through like the Verilog and actual hardware debugging yourself, so you gain all those skills yourself and ask questions that help you learn the specifics that you need. Because if we were to just give you the lab done, then there'd be no learning, right? And then instead of assuming previous knowledge, you guys want us to explain the fundamentals more, so that we can do. If there's anything that we just skip over, don't be afraid to ask a question. I'm sure like half the other people here are wondering the same exact thing. I know last year sometimes we'd go over things and I would just be afraid to ask a question. But if we don't ask the questions, then we don't know what the problems are that we're not covering. So just let us know. And then you wanted more work sessions, and I agree. I want to eat more pizza, so we will be getting that done more. I'll be calling Domino's a lot more this quarter. And finally, so this one was really interesting. You said you wanted to adapt deadlines around holidays, because I know last quarter with Thanksgiving and all, it was hard for some of you to complete things and you need to ask for extensions, but we will be taking that into account. I think there's only 2 Mondays off this quarter, which is sad, but makes it easier for us to schedule around it, but we'll keep that in mind. And if that's a problem, just let us know. Just when you ask for extensions, we didn't really care as much that like a lot of people are asking for extensions. We just want to know well in advance so we can plan around it, because we can't keep our schedule going. And if we need to keep some teams on track, it's hard for us to let other teams move on at the pace that we need. So just let us know about extensions well in advance. And thank you for all the suggestions. If you have any more, you can always tell us. We're always open to that. But let's move on.
So for today, we're going to be going over the basics of numbers and binary. Then we're going to move on to doing math on those numbers using arithmetic, such as addition, subtraction, multiplication. We're actually going to skip over division because it's a pain and it's honestly not in the scope of DAV. Then we're going to look at pipelining, which is a method to increase our throughput of our circuit. Then we're finally going to go over the first lab of the quarter.
right, so as usual, here's your timeline. We're speeding ahead along it. We'll be finally getting into math, which will help us with our fast Fourier transforms, which are also coming this quarter. But as you can see, we're just speeding along. Next slide, please. Same thing, just verbal or other visual format, textual format. And then Andrew's going to take us into some number theory.
All right, on to number theory. So we have binary numbers, which is essentially what we've talked about in lecture 1, where we have counts up using ones and zeros alone. This just counts upwards and it's unsigned. So you can see that there's not really any way for you to notate the sign of a number. But unfortunately, we have to deal with negative numbers all the time. Say like, you know, your bank account goes in the negatives, right? That needs to be taken into account. You can't just be put back at the max number of monies, unfortunately. Andrew, math itself, Antino, yes. So we'd want some sort of system where we would be able to store negative numbers and still be able to use the mathematical operations that we have designed for our unsigned number system. This leads us on to 2's complement. 2's complement has some really cool features to it, such as it has a sign bit, which is the most significant bit always notates the sign of the number. So if the most significant bit is high, is 1, then we know that the sign is negative. What's also great is that you could do all the mathematical operations that you would do with binary unsigned integers that you would do with signed binary integers. You can see that when we do represent something in 2's complement, we actually have to cut down the number of total possible positive numbers we have. So instead of 2 to the nth minus 1, 2 to the nth possible unsigned integers, we have 2 to the nth minus 1 of positive integers. And then we take the other 2 to the nth, and those are then represented as our negative integers. This also overflows in both directions, which is kind of a drawback. So you're going to see that if you get to too high of a positive number, you'll actually overflow into the most negative number. And then if you get too low as a negative number, then you actually overflow into the highest of the positive numbers, which kind of leads to a lot of errors. If you take in CS31, that comes out to be a big pain. Yeah. Some of 2's complement's advantage is that it's really easy to negate a number. So in order to negate a number in 2's complement, you would first not every bit, and then you would add 1. So that's done in 2 lines of system Verilog code, which is pretty nice. And you can see an example right here on the right where you have -7. We flip every bit and it goes to 1 0 1 1 0. Then we add the 1 and it goes to 1 1 1 0. This goes to 7. If you do the math, so 1 plus 2 plus 4 is 7. This actually allows us to handle addition and subtraction without edge cases, like I mentioned before. If you take an M16, then you know that the edge case would be that other number systems represent 2 zeros, which is a huge pain and we don't want. And 2's complement is the best number system we have to not represent 2 zeros and also store the most amount of information. Alrighty, on to basic math.
Yeah, so if you have any questions about the systems we just covered, please let us know. Again, these are just ways of representing numbers. So you're still gonna have a bunch of 1s and 0s, but it's just the way you're thinking about them. So if you haven't seen it before, let us know in the chat or raise your hand if you have a question. But we're gonna use this fact that 2's complement handles addition and subtraction without edge cases to do addition and subtraction. So let's go into some addition circuitry. So in binary, you can add just like you do in decimal, right? So on the right, you can see you can do the same thing, probably learned in like first grade. I actually don't know which grade you learn addition in, but that grade. And you can do the same thing along, but this time, instead of adding like 9 plus 1, you get 10, you carry that 1. Instead, you're going to add 1 plus 1, get 2, and carry that 1, because 2 is 1, 0. So that's all there is. And every time you carry a 1, and if you add 1 plus 1 plus 1, that gives you a carry of 1 and a sum of 1, right? Because 3 ones means you get to 3, and 3 is represented as 1, 1. So that the first one is the carry and the second one is the sum. So keep that in mind, because there's 4 cases of how you can add a 1 to 1 or 1, 0 in together. And that's what we're going to do. That's what we're going to keep track of to create a circuit for this. So that circuit is called a half adder. So here you can see we just took basic addition and turned it into a circuit, but by using the fact that there's only 4 ways to add zeros and ones, or 1-bit numbers, basically. So what you're going to do is take in 2 bits, let's say inputs A and B, and then you're going to get 2 bits out, a sum and a carry, which is the same, which we just talked about in the past slide, where for each column we were adding maybe like 0 plus 0, you get 0, and a carry of 0. And here, even though this table says sum and carry left to right, it's easier to think of it as carry and then sum, because your carry is going to be your most significant bit and your sum is going to be your least significant bit. So this is just the basic circuit to add 2 bits together, and it'll give you a sum and a carry. But one disadvantage here is it's called a half adder, because you can't take a carry in. So if you're adding like the second 2 bits of 2 numbers, then you can't take the carry from the first 2 bits on the right side. And that's why we need a full adder, which is here. So full adder is very interesting. It actually is built from 2 half adders. So you can see here, we use our half adder circuit and we connect 2 of them together, you get a full adder. And the difference here is you can take a carry in. So if you're, as I said before, if you're adding maybe the second 2 bits of 2 numbers, then you can take the carry from the first 2 bits and use them in the second half adder to create a full adder. So now instead of just 4 possibilities, there should be 8, because there's 3 bits you're adding together. So 3 combinations of numbers that create other numbers. Does this make sense? Actually, does anyone have a question about this? Okay.
Can anyone explain why we use an XOR and an AND in our half adder circuit? If you give a quick look at the table, does it make sense why you'd use why you'd use an XOR in a AND gate? Just speak up. I don't have audio or the raise hands thing on.
Because if they're both 1, it overflows to 0. If one of them is 1, the sum is 1, and then the carry is only 1 if they're both 1.
Right. Good job.
All right, perfect explanation. So we got our half adders, we got our full adders. Now what we want to do is combine a bunch of them to create an adder that can do more than just 1 bit at a time, right? We want to add bigger numbers. So here, even though the image is a little scuffed, you can see that when we add multiple numbers together, we have to cascade the smaller addition circuits. So on the bottom, you can see what's called a ripple carry adder. So essentially what it's doing is it adds the least significant bits, and then the carry ripples upward. So you use that carry bit to add into the next adder, and then that ripples up to the next adder, and so on from right to left. So you have to add at the rightmost side first, and then work your way up to the left, because you need to work from the least significant to get up to the most significant bits. And this is kind of similar to how we do, this is the same exact type of addition you do in decimal. If you think through every step of additions you do in your head, probably start at the least significant bit and then work your way up, or least significant digits. So like the 1s digit, and then work up to the 10s digit, then the 100s digit, unless you're just a god, you do it like all in parallel. I don't know how you pull that off, but if you do, let me know. but that's the same way to think about binary. Yes, and Brandon brings up a good point here that the rightmost full adder can actually just be a half adder. Here in this case, the full adder, the C in that bit would just be 0. Or you could do a half adder where it would just take 2 bits in and have no carry in, right? Because we don't have a carry into the least significant bit. And one thing to keep in mind here, this is going to come up later. So what's important here is that when we do a ripple carry adder, it doesn't happen all at once. The rippling has to take up some time, some delay. And that's a little combinational delay we have in the circuit. So even though this circuit is fully combinational, it can't exactly happen instantaneously. So in hardware, we're going to have some sort of delay. So just keep that in mind for later.
Alrighty, now on to subtraction. It's pretty much adding, but in reverse. So what you do is you just say A minus B is the same as A plus negative B. So when we talked about negating a 2's complement number before, this is where that comes really in handy, is where you want to subtract 2 numbers. So if you have 2 positive numbers, the second number which should be negated using the 2's complement negation. So you'd flip every bit and then you would add 1, and then you could add those 2 numbers together. Doing that, you could then use the same circuitry that you could use as a full adder, which makes, or as an adder circuit, which makes it really easy to implement. Or we actually do have our own subtractor circuits. So right here, you can see that this is the half subtractor, which looks really similar to the half adder, right? Except for this NOT gate here. This NOT gate then gives the behavior that only if B is high, we get the, what is this? This is the opposite of carry, so it would be carry down, I guess. I don't know what you would call it in first grade math.
It's the borrow bit, I think.
The borrow, there you go. Yeah, so then you have 2 half adders put together makes a full subtractor, and those 2 borrow bits are OR together right out here. Yeah. Now on to multiplication. So multiplication is really just adding, but over and over again. So if you see here at the top right, you add the first digit to the first digit to each of these, and then you carry, and then you add the second digit to each of these. Then you carry again, and then you add the third digit to each of these, and you get this number down here, etc., etc. Then once you're finally done, you could do all the addition right here, right? Gives a good explanation right here in steps. And Chintu, do you have anything else to say about this one?
No, so this slide, we have to make sure that everyone just takes a second and internalizes this, because you have to understand this and just straight up doing the math itself before we get into the circuitry. Because unlike the adder, this is gonna make 0 sense to you if you don't get how the multiplication is working first. Like when we start the circuitry, it's gonna just mash your brains. So if anyone has a question about this slide, you have to let us know now. If you look at the graphic image format, I'm just not gonna say it because I don't want to start a debate. But you can see how each line, as Andrew said, is being created. So you do 111, the top number times the least significant bit of the second number, right? Gives you the first row. And then top number times the second least significant bit of the second number gives you the second row, and on. And each one is shifted over, and that shift over, it just means there's a 0 at the rightmost place. So it's the same as all the multiplication we've done before. I don't know, is it called long multiplication? I have no clue, but in binary. So that shifting and the way this is working, the additions over and over is very important. But other than that, I think we're good to move on. Right. So before we actually get into the multiplication circuit, we have to deal with a couple things. So firstly, we have to think about the fact that we only have a certain number of bits we can use to represent multiplied products and factors. So a couple of things, we have some overflow conditions. I think I listed out one there. And because like, if you multiply 2 by 2 and get 4, but you only have 2 bits to represent 4, you can't represent 4. So then you get a 0 due to overflow. And then in addition, similar concepts apply to negative numbers. Even though addition and subtraction work well with negative numbers, this whole thing about like not knowing how many bits to represent our products with comes into a problem when we have negative numbers. Because let's say, so when we do this multiplication here, I tried it out myself. I may have done the math wrong, but when I did it in unsigned, I did it out, and 11 times 3 gives you 33. But then you try doing it in 2's complement, and then it's just kind of arbitrary. Like if I were to use all those bits to represent the number, it could mean negative 31. It could mean 33. Neither of those numbers actually make sense because negative 5 times 3 is 15. So we have to have a method of standardizing our product, the number of bits in our product, to make sure that we don't have any complications like this arise. So what is the method to standardize that, Andrew?
Sign extending?
What? Yes, Andrew. The next slide is about sign extending. Dang, confused me there. Okay. So as Andrew said, we need to sign extend, which I hope I put here. But first, we need to understand how many bits to use. So let's do a little example. If you take the largest numbers that are 3 bits and 4 bits long, 7 times 15, you get 105. And that requires 7 bits to represent. You can try this with any 2 n-bit number or m and n bit numbers, and it'll give you an m plus n bit product, which I guess you can test it out yourself, but for now, just trust.
Proof by trust me.
Yeah, if you want to do it yourself, that's not, like, you're a good mathematician. That's good on you. But for now, just trust. And what we know about this is that if we need m plus n bits to represent a product correctly, we should probably use m plus n bits at least, right? So on the next slide, we get to the multiplication method. And here is where Andrew came in about the sign extension. Thank you, Andrew. So when we want to represent all products correctly with negatives included, we need to first sign extend the factors to p bits. And here we just talked about how many bits you need, because you should pick the number of bits p based on your knowledge of like how big your number is going to go. So if you know your number is going to go to the highest possible, then you know you need to use m plus n bits. But let's say you're multiplying like all of your multiplications are just like 1 times 1 or 1 times 2, and you already have like 5 bits available. You don't need to use all those bits, right? Because you know the products are going to be super small. So picking p is up to you. But once you know that you picked p correctly, the number of bits you're going to use for your product properly, you need to sign extend both of your factors to that number of bits. So in this example, we're using -5 and -4. We're sign extending both to 6 bits. And sign extension just means you take the most significant bit and you write it out over and over again until you get the number of bits you want. Keep in mind, sign extend, you can't do it in the other way. You can't just chop off the top bits because then you're losing info. You have to add more bits. So don't just subtract bits. That would make no sense.
Basically, excuse me.
Yeah.
So basically, like under the most general method, like here, the -5 and the -4 were both like 4 bits. So generally you would be 8 bits like maximum, right? If you didn't know for sure, right? Or am I thinking wrong?
Yes, because m plus n bits, right?
Okay.
Well, yeah, I guess maximum, yeah, you'd only need m plus n bits. Sorry, I think I said minimum before, so that's a good catch. Max, you need m plus n bits.
Okay. Thanks.
Yeah, but we use 6 here because we know that 5 times 4 is not going to go above 6 bits, because you can represent 20 with 6 bits.
Cynthia, question. How is this? Do you have like 6 different adders to add each of the?
That's a really good question.
shifted numbers or what?
That's an amazing question, because that's what's on the next slide. This is just
What?
so this
No way.
method is just how we're doing the addition like conceptually, but the actual circuitry takes it. I mean, we'll show you step 2, which is multiplying the factors.
Any questions before we get off to the circuitry? Because that is a really good question, and it's really important that you guys have a really solid understanding of how the multiplication works before we get into the circuitry. It's kind of confusing, honestly.
Wait,
So
can you say what sign extending is again?
So sign extending is taking whatever your most significant bit is in your smaller value. So we know, for example, that -5 is a 4-bit number, right? So it gets cut off here. If we were to make this into a 6-bit number, which is here, we wouldn't want to put zeros here, which would be the default. We'd want to put 1, and that'd be the sign extending. Sign extending also has the benefit of keeping the numbers the same sign, even if you add more bits to that number. So for example, if I had this -5 and I put a 0 here, if we did the math, it would be 1, 2, 4, 8. So that'd be positive 11 if we didn't sign extend.
did that answer the question? Or
Yeah, and then we just ignore anything that all of the overflow bits, essentially like the ones on the left.
These little dot dot
Yeah.
dots.
Yeah.
Yeah, so we shouldn't have to worry about those because all the information we need to worry about is the m+n bits, right? That's all the information that we care about is stored. Everything else could just be garbage, and we don't really care.
right. So that is a good question. That's actually the last step of the algorithm. So first we sign extended the factors to p bits, right? We didn't cover the rest. So once you have 2 p-bit numbers, you multiply the 2 using a circuit we're going to show you, and then you take the lowest p bits. And you only need to worry about those p bits because the rest are just sign extended overflow that are like sign extended, not garbage, but just extra bits that we filled in anyway. So that information we don't really need anyway. But this will give you a number that like has the proper sign. Like you can see, multiplying -5 by -4 gave you a positive 20. Using another method may have given you, let's say, -20, for example. But this takes care of that for you. Any other questions about this method? Also, I think Brandon said there may be an error in the photo. I think the -5 and -4 might be switched because I remember I switched them at one
No.
point.
Can't be, because the -5 has to have an odd number, right?
Yeah, okay, that's what
Oh,
I. that's what I
no,
thought.
yeah, no, he's right, 'cause,
Yeah, that's what it is.
Okay, he's right.
Yeah, so the -5 and -4 should be switched. I think that's the issue. But other than that, I mean, we can both switch that in post, but other than that, the side should make sense. Yeah, so let's go on to the circuit. Okay, so Tyler, you asked us if we use adders to do each step of the multiplication, and you were correct. So here you can kind of see this is this little diagonal circuit laid out here, right? And on top, if you show the top row, A3 to A0, that's your first factor. And then on the left, you have B0 to B3 or B3 to B0, and that's your second factor. So right now they're both 4 bits. And that means our product is gonna be how many bits? Or maximum how many bits? 4. M is 4, N is 4. How many bits for all that part? Yes. So
Nice.
perfect. We need 8 bits to represent like the maximum possible. So that's why on the bottom we see P7 to P0. That's our product. Now, when you look at the circuit, first thing you'll notice is there's a bunch of AND gates. And so here, the interesting thing is if you AND 0, if you AND something with if you AND a 0 with a whole factor, it's like multiplying by 0 because everything goes to 0, all the bits. And if you bitwise and a 1 with your entire entire number, then you'll just get that number back, right? Because it's like multiplying by 1. Because 0 and 1 is 0, 1 and 1 is 1. So this and is actually what it's doing is it's multiplying A, the top line, by each bit in B. So you'll see each line that Andrew can point to here, like the B0 line, B1 line, B2 line, those are each feeding a bit of B and then multiplying that bit by every bit in A. Does that make sense?
Wait, what's the FA stand for?
Those
Full
are full adders.
It's a good question.
Maybe go to the next slide and then it'll make more sense to look at the. Right, so we have the two numbers 1110 and 0101, right? So think of the top 1110 as A and 0101 as B. And then here, what's happening is in each like line of full adders you see is adding two of the like diagonally shifted numbers together. So the first one is 1110, and that's created by ANDing B0 with A. So B0 is 1, right? The least significant bit of B is 1. And when you AND that with A, it's like multiplying by 1. So it gives you A back. So that is going to be underneath the AND gates at the top. So that's that multiplication. And then you add it in to the full adders that have just multiplied the second bit of B, so B1, multiplied by all of A. So that's where you see the first row of full adders. That's going to give you that that sum there of well, the first and second numbers. You also see that it's shifted, right? Because the second row of zeros is shifted over 1, and that's the shift you see in the circuit. Because the rightmost digit only gets the 0 from the top row, and that's just sent all the way down to P0. So that far, does that make sense? Or better question would be, does anyone have a question on that? You can let it simmer for a bit. Give some reactions or chat. Because understanding this slide basically is the hardest part of the lab, right? I think, other than the keypad.
Yeah, this is probably going to be the harder part. If you understand this in pipeline, then like the rest of this lab should be super easy for you guys.
Yeah,
It is a lot of moving parts. I totally agree.
We're trying to split it up into just thinking about the AND gates first to get each sum, and then the full adders are connecting the sums. So as long as you see how it connects to the numbers on the right, you'll be able to figure it out in the lab. But it's very important that you ask questions about this now, if you can, if you've thought of any.
If you guys kind of think of it as like a non-combinational circuit, you kind of think, okay, all these AND gates are being done first, and that's actually drawing out the numbers, right? And then after that, all these full adders are being executed, and that's what's actually beating the final answer. And if that helps you guys out any.
Okay, so hopefully that's simmered for enough time. If you have questions, ask us just anytime in the lecture. But we're going to go on. So there's another way of looking at the circuit. And this way, Andrew and I both, I think Andrew and I both think of it the other way. But there are some people in this world that just love chaos, but they also love other ways of thinking, which I think are great. And if you find this easier, maybe it'll help you. That's not an attack on anyone. I don't know who likes this method. I'll be honest. Maybe it's just better. I think. Do you have a way of explaining, Andrew?
Right. So I'm just gonna go ahead and say it's the same thing, but instead of diagonal, vertical. That's how David explained it last year. You see B0 here. Here's your first set of AND gates. You also still see that A0 gets carried all the way down to the product 0. Then you can see B1 gets ANDed with all of A's A, and that gets added together right here. And the way that this full adder right here works is you get Y0 added to X0, right? Y is one 4-bit number, X is one 4-bit number. I kind of got caught up on that last year as well. And then S would be your resultant, or your sum. So that'd be your 4-bit sum, and then Cout would be your carry. Then you also AND again with B2, put it through the 4-bit adder. So it's just like doing everything previously. It's just moving around a couple things and making less crossed lines. We'll do a vote later. Okay, Grace and David are the two people I know that like this one better.
If you have questions about this, just ask Grace then.
Yeah, exactly.
Sorry. I mean, we'll try to explain it to you. I'm joking. Kind of.
Nathan, does your brain hurt for this or for the other one? Or like, does it hurt for like the concept in general? Okay. Yeah, I kind of agree with you on this one.
After man's heart. Okay. Maybe we should just move on so we don't create a schism.
We'll hold a vote at the end of the lab, see which one they like better.
Yeah, that's true. But no more brain hurting here. Because like we said, we're skipping division, which yes, thank you. We know you love us for that. But you can also do division by just shifting bits. So now any number you want to multiply by or divide by a power of 2, just shift right or left. It's easy as that. Make sure when you're shifting that when you shift left, you fill in with zeros, because if you added ones, now you just don't add ones. When you add zeros, it doesn't add anything to the number. All it does is multiply by 2 when you shift left. And if you shift right, you want to fill in the sign. Right? Yeah, you want to fill in the sign, because if you're using a negative number and you just filled it in with a 0, suddenly your number is positive, and that would not be a positive thing to be doing, because now you just screwed up your number. So kind of like sign extension, when you shift right, make sure you fill in the, I think that's called, that's arithmetic right shift. If you're doing logical right shifts, you can just shift bits to the right and fill in zeros, I think. Is that correct?
Yeah. Logical right shifts are useful, just not in division. Definitely use logical right shifts in other ways.
Yeah, I think it's for like priority encoders and stuff.
Yeah.
Yeah. So we're gonna be using arithmetic right shifts. Keep that in mind. That should be the three greater than signs instead of 2. And a little property here: when you shift down, an odd number, you're probably thinking, wait, I can't divide an odd number by 2 without some truncation. You're correct. Truncation works a little weirdly though. Whenever you shift to the right, your number will always round down towards negative infinity. So if you have a positive number, it'll round down. And if you have a negative number, it'll get even more negative, like the number will be even more negative. So you have put some examples there. 2.5 will round to 2, and negative 2.5 will round to negative 3. And you can see here, negative 105 divided by 2 would be negative 52.5, and then that becomes negative 53.
Alrighty. So we have a quick little question. What's the trick that we use to multiply 2-digit numbers by 11?
This has nothing to do with digital logic. I was just hoping to take a break so your brain stopped hurting.
This is fun 1st through 3rd grade math, according to Achinthia.
I don't even know which grade this is from, as I said.
You have 3 numbers. The one on the left is the upper digit, and then the one on the right is the lower digit. I don't know what it is. And then the one in the middle is the sum.
Nice. That would be correct. And as we pause on this slide, I mean, first of all, congratulations to everybody that answered that. Good job. I actually didn't know how many people learned this trick.
I did not.
Yeah.
I did
See,
not either.
see, everyone has something to learn. See, not everything has to be Verilog, you know? Actually, I mean, with me it does, but for other people not. Anyway, as we pause on this slide, we can also, Raj, I just said not everything has to be Verilog. As we pause on this slide, we can also ask other questions if you have any. So it's supposed to be a break, but now Raj has made a Verilog.
Raj, just for you, you can go ahead and implement this as a special case in your multiplier circuit. And
That's right. And one more lab bug to you. If you implement this, your multiplier only does 11, but it's a feature, not a bug.
so what's the final answer to this actually? So it's 5. Something needs to do with 5, but
No, the final answer is 352.
what?
Andrew.
No. That's crazy.
It actually works for any two-digit number.
Wow. Okay.
Yo, wait, who knows the trick for one-digit numbers multiplied by 11 though? This one's big. Guys, if you don't know the one-digit number times multiplication by 11. That's tough. Well, I don't know it either, so I guess we just move on here.
Yeah, I guess. All right.
Pipelining. All right, last year there was a picture of Sonic on the slide, but my friends say Sonic is cancerous in Smash, so I didn't put Sonic on the slide. But you can see in this graphic here, I can't start a war by saying GIF or GIF again. So this graphic here, the moving graphic, you can see things going through steps over time. That is pipelining. So how are we going to use this to boost our Fourier transform later on? Let's see. Yeah, the scup Sonic, that thing's scary. Okay, so first we need to talk about two things, latency and throughput. Latency is the total time taken to complete one operation. Throughput is total number of operations you can complete in some time. So this nice little image, you can see the latency. One packet is being sent through. How long does it take? That's latency. Throughput, how many operations are we sending over a certain amount of time? It's very redundant, but okay. So now that we know latency and throughput, how is pipelining going to help us improve these? So basically what is pipelining? All we're doing is splitting, kind of like a factory line like we talked about before. We're going to be splitting operations into smaller tasks. So here images talk about laundry. If you do every laundry cycle one by one, it's going to take you a lot of hours. But let's say you split it up. So you do washing, then drying, then folding your clothes, all in parallel with each other. Then that's pipelining, and it makes your whole process go a lot faster. So how does this affect latency and throughput? I think that's the next slide. Yeah. So why do we want to do this, right? We're already having a great time just doing everything one by one. Why do we want to make it harder on ourselves, figure out how to do it all at the same time? We want to increase throughput. So when we pipeline, we're doing things in parallel, right? That means we can get one more step or multiple steps done at the same time, but one more operation done in like every time step or every cycle. And that makes it better because instead of waiting maybe three cycles for our laundry to complete, every cycle we're just pumping out more laundry. So now you're getting a lot more laundry done in a lot less time, and you're just more efficient. That's why we want to pipeline. But you can't just go around and pipeline everything because there's also some disadvantages. Let's say we add so many pipeline stages that each stage is now taking like some set amount of time, right? But now you have to add up all the pipeline stages as time, and it might actually be more time than the actual process takes because every pipeline stage is actually dependent on the one stage that takes the longest time. So like, let's say the dryer takes an hour, washer only takes 30 minutes, and then your folding takes like 2, right? Or sorry, like 10 minutes, let's say. But then in every step, you got to wait for your dryer to complete before you can put more laundry in from your washer. Now you've just incredibly slowed down your entire process that maybe could have been faster with, I mean, in that scenario, if you did one less stage, it wouldn't really make sense. But let's say you split it up into like multiple washer stages or something. And it just makes more sense to have one washer stage because it's already the smallest one. So you got to think about when you're going to pipeline. So the best case to pipeline is when you have multiple operations that are complete. Like when we make this calculator, we want to run additions over and over on top right after each other. That's a good case to pipeline because then you can run multiple steps of the operation at the same time. Well, it makes more sense for multiplication because multiplication has all those addition steps, whereas addition is just one addition. But having those smaller steps is what matters. So you have to make sure that you have a lot of steps. They're all small and they take around the same time to complete, because you see in like a computer example later, you have one step that takes like, I don't know, 900 time steps and the others are all taking 10 each. Then that 900 one is just going to slow down your entire pipeline. So you got to make sure that one can be split down. So just when you're pipelining, you got to think about these disadvantages. And here's a summary here. The easiest way to think about it is that when you don't have a pipeline, your latency is super small, or is generally smaller, because you're not waiting on each pipeline stage to finish to get your whole operation done. So if you just have one load of laundry, there's no real point in pipelining because like you're just waiting for, I mean, you're not really waiting for anything in that case, but like, what's the point? There's nothing for you to even run in parallel, right? So why would you like split it up? And then your throughput though is lower because if you have multiple things you want to run, you have to wait for each one to finish. So like every operation has to finish before you put a new one in, instead of just doing pieces of that operation side by side. Meanwhile, if you pipeline, the exact opposite is true. Your overall latency increases because every pipeline operation has to go through every stage. And if your slowest stage has to happen, like let's say 5 times because it's a 5-stage pipeline, then suddenly you just increase the amount of time that each of your operations uses. But your throughput does go up. So there's this trade-off between latency and throughput they have to keep in mind based on what kind of operation you're doing, which one you care more about. So finally, we have some visuals for this, I think.
Right, kind of zoned out. Okay.
All right, this is very well, let's say I'm grateful to my M151B professor for providing these slides that show why it's useful to use pipelining in processors. So in computer processors, if you try to execute a whole instruction at once, then it makes it easy to do a lot of steps. I'll give you that, but it's going to slow down your computer processor because now you're waiting on every instruction to complete before you do a new one. But let's say you pipeline them, and suddenly you're decreasing the time that it takes to do multiple instructions. So like in the right image, you can see that it takes 800 picoseconds to run each operation. Meanwhile, on the bottom one, it takes you like in every 200 picosecond cycle, you're just churning out one more instruction. So suddenly your pipeline is just making your entire processing 4 times as fast. So that's the power of this. And yes, I did take it from a book, but it says Sam Willie at the bottom. Therefore, it's not straight plagiarism. It's just half cut Sam Willie. Plus, like, why reinvent the wheel? You know, they already invented it.
Alrighty, now on to our pipeline addition example. So this is going to be kind of similar to, yes, we are plagiarizing this from you, David. This is going to be very similar to our pipeline multiplication that you're going to be doing in the lab, so pay close attention. So here is our pipeline parallel adder. You can see we have A, B, C, D, E, F, G, H. These are all 4-bit numbers that we want to add together and have the answers as quickly as possible. So first, let's start with A and B. We're going to put A1 and B1 through the full adder right here, and that's going to give us X1. Then we're going to move the rest of A and B right here. I like your background, Brandon. We're going to move the A1 and B or A and B to these new registers and store the result of X1. Then we're going to add B2, and on the same clock cycle, add C1 and D1 together. So now when we go on to the next clock cycle, we can see that we have the result for A and B and the result for C and D right here. And we're going to start doing the first bit of E1 and F1, the second bit of C2 and D2, or the second bit of C and D, and the third bit of A and B. So if you see here, essentially what we're doing is we're just going bit by bit and through each of our additions, as well as starting the next addition on the previous bit. So now we can see, okay, now we get X3, X2, X1, and we still have to add in the last to get X4, X3, X2, X1. So now we have the full answer for X3. And what's awesome, what's awesome is that the next bit, the next clock cycle, we get the answer for Y1, Y2, and we get the answer for Y. And then the cycle after that, we get the answer for Z. And the cycle after that, we get the answer for W. So instead of waiting for all this time to process X all the way through, and then we have to wait to process Y all the way through, and then process Z all the way through, we get them on new clock cycles, which increases our throughput at the expense of our latency.
And I have a question for the audience on that. Yes. Wow, Grace is just a beast. What are the purple boxes? Can someone answer that?
Like buffer registers or something?
Yes, nice. So you want to pass along your, what are the two things you add together called? Add-ins. You want to pass along your add-ins through the registers to each stage. That's what like G2H2, G3H3, all those things are. Because in each stage you gotta keep track of which numbers are being added, right? So yeah, it's a great question. Those registers are keeping track of the numbers being added, and then finally the sums that you're getting at each step. All right.
Any other questions? Why do you need what?
Yes.
X1, Y1, and Z1 are literally doing nothing. Just pass out when you're done. No. So the reason why you can't pass it out when you're done with the full adder is because you have to be able to show the result at the same clock cycle. So you actually do need these registers here, these three, to act as a buffer so that it follows the same path as here, right? So if we just pass it out as soon as it was done, we'd get something like, as our final result for A plus B, we'd get X4, Y3, Z2, W1, and that's definitely not what you want, right? You want to be able to store your previous values that you got. We'll still be able to process the new stuff that's coming in and store that as well. That is a good question, David. Great job.
All right, got a lot of great questions on this slide. Any more? All right, so how do we do this in Verilog? That was Q for next slide. Okay, so in Verilog, we want to do the same. We want to use the good old reg keyword for our registers again and update them on clock ticks, right? So in this image, you can see that you have each stage, which is going to be a combinational block, purely combinational. All it does is take an input and give you an output. With some delay, we're just going to not worry about delay, assuming that you're clocking your system at a speed that's slower than the time it takes for each stage to complete. And then each register is going to take your output from a previous stage and store it for the next stage. So this is where your pipeline happens. In that first slide, you saw the image of the bubbled letters passing along. Those are those stages. It's basically what's happening here. At every clock tick, you're going to update each register with the output of a previous stage, and that's how you pass along the value. So in the pipeline adder thing we saw before, all those registers you saw in each row, each purple row is one of these, like R1, R2, R3. And so for that, we're going to be using registers in Verilog, same old always at blocks that are clocked, but every stage in between is going to be either a module or some sort of combinational logic, maybe some assignment statement that you use that just takes values from at each input to the stage and gets you some sort of output. So like in our multiplier, maybe we're gonna do some sort of like splitting where each step in the multiplier has to be like each bit in the second factor is its own stage, right? So each register has to keep track of which like multiplied product we're at until we get to the final output product. And with that, the concept part of our lecture is concluded. We must get on to our spec.
Alrighty, so this is lab 5. We're going to be starting off with our simple arithmetic. So you guys are going to be making addition or half adder, full adder, a subtractor, a multiplier, and then a bit shift divider. So divide by a factor of 2 module. Then we're going to be working on pipeline practice, which is going to be where you guys are going to do a pipeline multiplier. So you're going to take whatever you learned from your stuff making the simple arithmetic stuff and make a pipeline multiplier. Then in checkpoint 3, we're going to be making a whole calculator. So this is going to be where state machines come into play. It's going to be really cool for those one team that did the state machine project. And we're also going to be trying to get the keypad to work if it does end up working. All right. Will we be able to do 32 times 11? I think we will. Yeah, we'll definitely be able to do 32 times 11. Raj as well, for sure. That's true. David, that just means you're better than a computer.
Right. If you can do your math in your head, that's a good first step to being able to reproduce it on a computer or on a FPGA. So that's good. That's very good. If you can't do math in your head, that's very relatable, and get well soon. That concludes our lecture for today. Unless you want to, we have some reference slides for the keypad that we'll be updating later. We'll fix we'll fix the issue with some of the slides later and post this recording as soon as we can. Thank you to David for helping record. Does anyone have any questions before we conclude? It can be about anything. If you have any like kit, we won't be needing hardware for the lab until week 3, hopefully, because our checkpoints are going to be due every Monday from now. And so we're hoping that by week 2, everyone will be back. Work sessions. Oh yeah, since we're online anyway, we can host Discord work sessions if you want. Are people interested in that?
We can't ship you guys pizza, unfortunately. It'd be too much of a pain.
Yeah, Andrew will call your parents and tell them to make you food or something.
Yeah, I'll be like, hey mom, hey Mrs. Chung, hey Mrs. Wong, please make food.
If the lab is closed, how do we get access to the FPGAs? Right, so our PLMs are gracefully allowing us to let people come by and pick up kits. Just DM us and we'll give you times that they're available. And as
You
long
guys
as the team
shouldn't need kits until after week 3, and hopefully we will be at least hybrid by then. Proof by trust.
Alrighty. Well, thanks for coming out. I know the Zoom lecture is a lot less, well, maybe it's more exciting. I don't even know. But yes, come to GM tomorrow and we'll be seeing you around, hopefully in person again. Good luck on the lab. And Happy New Year to everybody.